This is part 2 of class review from Thursday, May 7th, 2020. These are things we've done in the equilibrium unit. I'll just run through these again real quickly. So we've talked about rates of reaction. Of the 5 things that affect rate of reaction, the one that we use most often in the equilibrium unit is concentration. We talked about what is equilibrium, and equilibrium is equal rate of exchange. And we did calculations where these are the more basic and easier calculations where you find the constant given the equilibrium concentrations, or you find the equilibrium concentration given the equilibrium constant and some equilibrium concentrations. We'll make that a plural. All right, we also talked about Le Chatelier's principle. That was on Monday, May 3rd. No, 4th maybe, whatever Monday was. And the systems at equilibrium will stay at equilibrium forever until there's a stress, and if there's a stress, they shift. Equilibrium shifts away from an increase, and equilibrium shifts toward a decrease, except for pressure. And for pressure, increasing pressure causes a shift to the side with less moles, and if you decrease, it goes to the side with more moles. Then the 5th thing we did were calculations given initial concentrations, that's not equilibrium, and that required us to express the amount that reacted in terms of x. And sometimes you need a quadratic equation to solve for x, and we did that in yesterday's video. And today we're going to look at 2 calculations. We did solving for K using initial concentrations and 1 equilibrium concentration. That was the first video. Now we're going to take a look at something called reaction quotient, which we commonly call Q. We're going to compare Q to K to determine which direction the reaction is going to proceed on the way to equilibrium. So here's some problems about that. And I might mention while I'm thinking about it, you can always say show answer on these problems, and they'll show you how the answer was obtained. Okay, so let's get started with the question. We'll make a new problem here. Okay, so we have this equation COCl2. Get that out of there. COCl2, and that turns into CO and Cl2. All right, this is an equilibrium thing. We're given in this kind of problem, we're given the initial concentration. So you see we got the 0.398 molar. Out of the COCl2, we've got 0.231 and 0.231 for the other two. 0.231, 0.231. So these problems are really straightforward. What you're going to do is pretend you're just throwing all this stuff into one container. So you got a container sitting here, and you're throwing all the stuff into the container. And we wonder, is it at equilibrium? If it is at equilibrium, if I set the constant up like this, Kc is equal to the concentration of CO multiplied by the Cl2 divided by the concentration of the COCl2, and plug in the numbers, 0.231, 0.231, nothing is squared or cubed here because there's no coefficients, divide by the concentration of the COCl2, which was 0.398. All right, so let's find out this answer real quick. So 0.231 times 0.231 equals, divide by 0.398 equals 0.134. Okay, so 0.134, now we're going to compare that to the number I'm going to write in pink, which is 5.94 times 10 to the negative second. See it over here on the left side in the problem? So K tells us it's 5.94 times 10 to the negative second, or 0.0594. All right, so is this number that we're given, that's the known K, is that equal to the 0.134? That we call Q, the reaction quotient. Quotient because we're dividing products divided by reactants. So they're not equal. So that tells us that this system is not at equilibrium. So then the next question is, which way will the reaction move to get to equilibrium? Since this number is too big, it's way bigger than this number, it needs to get smaller. Would you make it get smaller by increasing or decreasing the numerator? Well, let me show you what I mean by that real quick. If I have 4 divided by 1, that would equal 4. Now if I make the numerator get smaller, I'm just going to make it get smaller by reversing them. So if I made that 1 and this 4, then that would be 0.25. So you see as the numerator got smaller and the denominator gets bigger, the ratio goes down. So if I want to make this number get smaller to match that number, whoops, so you can see it better. If I want to make this number get smaller to match that number, then I'm going to need to make the ratio go down like this. So to do that, I need to make less of the numerator and more of the denominator. So since the numerator is the product side, I need less product and more of the reactant side. That's the denominator. So if I'm going to make less product and more reactant, the reaction has to proceed to the left. So it's going to go from right to left. All right, one more problem. So in this problem, same kind of question. I'm going to find the reaction quotient and decide which way it moves. So we have the equation is 2CO plus 2NO. On the other side, you've got a CO2 and an N2. And you have to have a 2 in front of the CO2. All right, so in equilibrium situations, we've got the CO concentration is 0.408. And the NO concentration is 0.356. The CO2 concentration, 0.263. And the N2 concentration is 0.0993. All right, so our equilibrium constant, Kc, that's going to equal the CO2 concentration, that'll be squared, multiplied by the N2, divided by the CO, that will be squared, and by the NO, which is also squared. Plug the numbers in, CO2, 0.263 squared, N2, 0.0993, not squared, 0.408 for the CO, that'll be squared, 0.356, and that's squared because of the coefficients. All right, so now we do the math. 0.263, that was squared, times 0.0993 equals, divide by 0.408 squared, and then divide again by 0.356 squared equals 0.32. Okay, so that's Q. That's called the reaction quotient. We'll call it 0.33 actually. All right, so then go over to the problem here. And we know that K is 2.28. So K equals 2.28. Q, 0.33. All right, so how do they compare? Well, Q is too small. It needs to get bigger. So if it's going to get bigger, then I've got to make the numerator get bigger and the denominator get smaller. So the reaction will proceed toward making the numerator bigger. The numerator is the product, so it's going to proceed to the product. So we'd say it goes left to right. And we got it right. All right, so that is how you do a Q compared to K kind of problem. Now I'm going to post some problems to try. Watch the video, try the problems. And tomorrow on Friday, May 8th, is a Q&A day. Monday we'll have new content.